Hello, so in the video that we did a couple of days ago, we differentiated the function modulus of tan x. And the result we got when we did that was two lots of cosec 2x multiplied by the modulus of tan x. We got that result a couple of days back. So in today's video, we're going to differentiate this function here. So the natural logarithm of the modulus of tan of x. So yeah, we're going to use this result on the right-hand side to help us out here. But first of all, let's just consider the domain of x values in which this derivative will be defined for. So obviously these natural logs, we have to make sure that this variable there is greater than 0. So we need the modulus of tan x to be greater than 0 in order for this derivative to be defined. So where is the modulus of x? Sorry, where is the modulus of tan x greater than 0? So I mean, we looked at this a couple of days ago. So a modulus of tan x graph kind of looks something like, I mean, roughly something like this with the asymptotes there, another asymptote there, so on and so on. So you got these asymptotes at odd multiples of pi over 2, so 3 pi over 2 there, minus pi over 2 there, and so on and so on. So yeah, this so the x values in which this this modulus of tan graph is greater than 0, well, it's going to be at these at all the x values apart from basically multiples of pi over 2. So yeah, so this is defined for well greater than 0 for so true for x values in the real numbers, but apart from multiples of pi over 2, so k times pi over 2, where k is just any integer. Of course, it can't be pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, and so on and so on, just because we get these asymptotes at that part of the graph. Yep, so this would be our domain for this for this derivative to hold true. So now let's use the chain rule to differentiate the function. So now we're going to differentiate ln of the modulus of tan x. So yeah, this is going to be a chain rule example. Let's just make a note here that we're using the chain rule. So yeah, this is just the same as differentiating ln modulus tan x with respect to modulus tan x. So d modulus tan x. And then multiplying that by the derivative of the modulus of tan x with respect to the variable x. So yeah, we know from the previous slide then, or the video we did a couple of days ago, that when you differentiate the modulus of tan x with respect to x, you get two lots of cosec 2x times the modulus of tan x. So we know that. So we'll just write this over here actually. So two lots of cosec 2x times the modulus of tan x. And then this first derivative here, so differentiating the natural log of this tan absolute value with respect to this tan absolute value, well, that should just be 1 over tan, the absolute value of tan. So 1 over absolute value of tan x. And that's just because when we differentiate the natural logarithm of a variable with respect to that variable, we get 1 over the variable. So just using that fact there, we're just applying this fact down to here too. So then, yeah, we're just going to multiply the two results together. So 2 cosec 2x multiplied by tan x absolute value divided by the absolute value of tan x. Of course, these will just cancel out there. We just cancel that out. And so as a final result, we get this. So 2 lots of cosec 2x. So yeah, so in conclusion then, when we differentiate this natural logarithm of the modulus of tan x, we get just 2 lots of cosec 2x. And yeah, that is our final result for the video. But of course, yeah, x must be a real number, but it must not be a multiple of pi over 2 in order for this derivative and this function here to work. So yeah, so x can be any real number, but it can't be these multiples of pi over 2. So yeah, that concludes today's video.